Hello. So in this demo, I'll explain the keras and TensorFlow and how to use it in deep learning, and and to create a production-ready code out of it. So because we have gone through the basics, now we'll see how it can be used in a production-ready. So yeah, again, why TensorFlows versus NumPy? Because TensorFlow has GPUs utilization. It has TensorFlow serving, TensorFlow Lite. These are server uh, deployment ready uh, usage, and it, it has complete ML system, whereas NumPy is scientific. And what we'll learn is we'll go through the fundamentals again: Einstein and summation, gradient tape magic, and yeah, how to build neural networks from basics, and then how to call the more advanced functions. And yeah, so initially this is just the setup thing. Again, the same thing. How tensors look, why do we use tensors, what are the superpowers. So GPU acceleration, automatic differentiation, immutability, lazy executions. These are the kind of operations are are allowed in TensorFlows. That's why it is more favorable when we are working with a larger data set. And again, how to create it. Here also the basics. We can create from list. We can create them from NumPy arrays. We have special type of tensors, which is all zeros, all ones, identity matrix, and we can create tensors in a range format as well. So that is the options. Data types allowed are float 32, 64, 16, brain float, integer 64, int 34, like that. So all these are used in, and here are the usage when at what time you want to use. Then we have device utilization. So if it is not attached to the system is not attached to any GPU, it will take the CPU. But if it is, then it will take the GPU, and it will run everything on your GPU machine. Then some operations, it's element wise operations, but addition, subtraction, multiplication exponent, square root exponent, and the trigonometric properties is also there. We can also transpose a matrix. We can do a matrix multiplication. We can inverse a matrix as well. Yeah, so these are the operations which are we have gone through it, so I'll not go more deep into it. And we can again reshape the tensor to a particular format, and we can yeah, and the broadcasting is also allowed. um, we have gone through it in detail, so I will not again explain that. But then Einstein sum is one of the most powerful functions in TensorFlow. It can express matrix multiplication, dot products, outer products at the very complex functions. And we have seen how it can be, you just have to give the subscript what you want to do, and it will just do in the backend. So there should be a cheat sheet for it. Let me just so when you want to transpose a matrix, you just give this comma the matrix. You do this, and yeah, this is all column sums, row sums, diagonal, trace, element wise, matrix multiply, matrix vector, like that. So major complex problems can be just you give them like this, and the vectors on which these actions has to be performed, and it will give you the output. So yeah, then we have gradient tape. This is where the magic of automatic differentiation comes in. So there are no manual gradients being calculated. It gets calculated automatically in TensorFlow. For that we use gradient tape. So it calculates the uh, 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 partial derivatives and the gradients automatically. So you don't have to do every time because it's a complex process. So it under the hood it uses vectorization and very fast calculations to find it, and then it is optimized for it. And then yeah, how the matrix will look like, it's just an example. Okay, earlier it was like this, how the dy by dx will look like given this is your x. So if your y is x square, the dy by dx will be 2x. And how the output will look like is this 2 times all the values of x. So we just got these values. um, and So by default the tape is deleted after one gradient call. Use persistent equals to true to call gradient multiple times. So in the earlier, in the PyTorch case, what was we had to set it to false, requires grad. We had to set it to false to reinitialize it. But here it's ulta, it's opposite, and it's you have to um, it automatically, after one call, it automatically deletes the gradient, so you don't have to reinitialize it. And yeah, so basically PyTorch and TensorFlow keras are very similar. It's just some they both do the same thing, just few functionalities are different and syntax is different. So it depends on what you want to which library you want to work with, which framework you want to work with, and all the majority of the things are same, and both of them are powerful. So yeah. Then it's the visualization of the gradient. Yes, so this is the f of x, and these are the iteration. So over each iteration the f of x is reducing, the loss is reducing. And so we just want to find the lowest point. This is the loss and this is the gradient descent. So we want to find a point where it is the gradient descent is the minimum, so we have the minimum loss happening there. So yeah. Then we have same activation functions, like we have, okay, here we are creating on our own again, like we did in tensor PyTorch. We are creating it from scratch. We are creating our sigmoid function tan relu leaky relu softmax, and then we have our mean square error loss, and binary cross entropy loss, and categorical cross entropy loss. Binary cross entropy is for binary classification. Categorical cross entropy is for multi-class classification problem. So this is we have created. Now we are creating our own neural network. So in that we are initializing the layers, the activation name, and initializing the weights and biases. And for each layers we are computing the weights, random weights to it. And then in the forward we are just doing what our layer wants to do. So first is to do a linear transformation, is whatever the output is we have to matrix multiply it with the weights and then add the bias, and whatever the output is we have to pass it through an activation function. So this is what we want in our layer. We have initialized it over here, and it is running over the loops, over a loop for multiple times. Yeah, so that is pretty much it. So this is how we created a very basic form, very from scratch. Now let's see if it solves our XOR problem or not. So we'll use the same neural network, and we'll see if it works well or not. So from the beginning only you can see the accuracy is 1 and the loss was 0.1%. but accuracy is 100. But as you increase the epochs, it the loss is decreasing, and it is able to yeah, it is able to find reduce the loss, and it is able to predict the XOR values very efficiently. So that is how, and we have seen that it is very difficult to do with a single neuron, but yeah, using a proper layer, it solved that problem. uh, Now let's use high level keras API. So yeah, we'll just we did the manual weight initialization, but we can use layer.dense. It handles, it creates the random variables on its own, and manual parameter list we had to pass, but in model.tree enable variables, it will calculate the important variables. And we did for in the earlier case, we did calculate the gradient manually. What now, this model dot fit is where we it will automatically call the gradient function and calculate your gradients for you, so you don't have to do it. And we did manually update our weights, and for that we have optimizers, and it will, based on your gradient values, it will go back and change the weights accordingly. And yeah, and yeah, Kera's new feature is it works with, multiple backends, like with TensorFlow, JAX, and PyTorch. It has cleaner, more Pythonic way of coding, and it has better performance. So yeah, let's see how we can use it. So when we are creating, this is a sorry, let me fully connected layer. This creates layers.dense creates a fully connected layer. So we want 2 units, and the shape is 3 cross 1. Excuse me. uh, then this is x is just random values, and we are just passing the x to our layer, and we're getting the output. Now let's see how the output looks. Yeah, this is how the output looks, and this is the using the manual function. So you can see the values are same, almost like they are same. So it means like whatever we created primitively was correct. Now let's say we have to create a sequential layer. So yeah, again, in the PyTorch we did use that nn.sequential, and then gave all the layer details, whatever, how many layers we want in the between. But here also we can do this sequential layer. We just have to point layer.dense, and how many nodes it should have, the activation function, then how shape of input size, inner layer, how many neurons, what activation function, again the output layer, how many neurons, in this case it will be one, and the activation function. And this we are we are creating a model L2, and we're calling as sequential. Okay, this is an alternative way. One is you can pass it in one go, other is you can just do dot add and add one after another. So yeah, that is it. So yeah, it basically becomes very easy using the inbuilt high level APIs available. uh, yes. Yes, again, now I think using that we are creating our doing that same thing in XOR operation and different classifications model. So for XOR it worked well. We can see the loss dropping after a few iterations. This is the moon's classification data set, and here also you can see the train loss going down, and the validation loss also going down as the epochs are increasing, and the accuracy is increasing as the epoch values are increasing. It means the iterations are increasing. So, and in the moon case, see, it is able to find the boundaries, these complex boundaries as well, very well. So that is the case. Then we have digital digit numbers, and we are able to classify those images. And here also you can see the loss is dropping as the epochs are increasing, and even after in the validation set, again the training set and the test set, the accuracy is uh, going towards 100%. And yeah, this is how the data looks and just the predictions of it. So yeah, that is pretty much it. Now it's just explaining what the best practices are. uh, so now we have to normalize the inputs before. So to avoid having the weights of very higher range, so that then we'll have the problem of exploding radiance. And if the weights are really low, then we can have the problems of vanishing radiance. So we have to normalize our inputs. um, we have to start simple and add complexity as needed, and use dropout for regularization. Batch normalization can speed up training, and relu for hidden layers. Yeah, so these are the some best practices. Thank you.